Hi students, today we'll speak some more details about capacitor. Before going on to the capacitor, in our previous session, in the charge sharing of two conducting spheres, I made a careless mistake and hope that you have identified that mistake and rectified it. Okay, then let's move on to the topics that we are going to discuss today. We are going to discuss about parallel plate capacitor. Okay, then moving on to a parallel plate capacitor, you could see a diagram over here. These two sheets are two parallel conducting sheets. This is one sheet and this is another sheet. They are conducting sheets which are parallel, and these two sheets are connected to a battery. This arrangement is called a parallel plate capacitor. The arrangement of two parallel conducting sheets kept between an insulating medium, it is called as a parallel plate capacitor. What's a parallel plate capacitor? It is an arrangement of two parallel conducting sheets kept between an insulating medium. That is, there is no direct contact between these two sheets. Okay. Now, this is our parallel plate capacitor, and we have to understand the capacitance of a parallel plate capacitor. In order to say about the capacitance of a parallel plate capacitor, let's look at this diagram, and from this diagram, this sheet is connected to the positive terminal of the battery. Therefore, there will be an accumulation of positive charge on this sheet. Can you understand this? Okay. And since this sheet is connected to the negative terminal of the battery, this sheet will have a negative charge accumulated over it. Is that clear? Then there will be an electric field between the plates of the capacitor. In order to say about that electric field, let me say the area of this sheet is A and the area of this sheet is also A. The two sheets are of same area. Then the distance between the two sheets, it is D. D is the distance between the two sheets. A is the plate area of the sheet. Clear? Then let's find out the electric field between the two sheets. For saying about the electric field between the two sheets, we will draw a diagram over here, and if we are having a positive charge sheet over here, we have learned in our first chapter the electric field intensity due to a single sheet, it is E is equal to sigma by 2 epsilon. You have learned it as the application of Gauss theorem. Can you recall what sigma was? Sigma was surface charge density. Hope you know this equation. This is the electric field intensity due to a single sheet. And if I am marking the direction of electric field intensity, to the right of this sheet, the direction of electric field intensity, it will be like this. And if I am calling it as our first sheet, then this should be the direction of electric field intensity. Is that clear? What's electric field intensity? It is the electrostatic force of attraction or repulsion felt by a unit positive charge. That means if I am assuming a unit positive charge over here, this sheet will repel. Therefore, this is the direction of electric field intensity due to this sheet. Hope it is clear. And if I am marking the direction of electric field intensity due to this sheet over here, then it should be like this itself, and it should be E1 itself. Clear? Then what's the direction of electric field intensity due to this positive charge sheet over here? It should be like this. That is, it is E1, and if we are placing a unit positive charge over here, this unit positive charge will feel a repulsion. Therefore, the electric field intensity like this. Therefore, due to this positive charge sheet, we will have electric field intensity like this. Then let me introduce a negative charge sheet over here. That is, if I am placing a negative charge sheet over here, and this is a negative charged sheet. Due to this negative charge sheet, let me mark the electric field intensity. We are not considering this positive charge sheet. We are just considering only the negative charge sheet now. Therefore, let's call this sheet as sheet 2. And due to this sheet 2, what's the direction of electric field intensity over here? In order to find out the direction of electric field intensity due to sheet 2, we have to assume a unit positive charge over here. As we have learned, electric field intensity is the electrostatic force of attraction or repulsion felt by a unit positive charge. That was the definition of electric field intensity. Therefore, if I am placing a unit positive charge over here, this negative charge sheet, will it attract or repel? If I am placing a unit positive charge over here, this sheet will attract. Therefore, this is the direction of electric field intensity due to the sheet 2. And since it is due to sheet 2, I am marking it as E2. Is it clear? Then, what's the direction of electric field intensity at this point due to this negative charge sheet? That is due to sheet 2. If I am placing a unit positive charge over here, this negative charge sheet will attract. Therefore, this is the direction of electric field intensity. Clear? And if I am marking the direction of electric field intensity over here due to this sheet, that is due to negative charge sheet, you just don't consider this positive sheet. Now we are marking the direction of electric field intensity due to the sheet 2. Therefore, assume a unit positive charge over here, and what will this negative charge sheet do? The negative charge sheet will attract the unit positive charge. Therefore, this is the direction of electric field intensity, and since it is due to sheet 2, I can mark it as E2. Therefore, if you are looking at this diagram, between the two sheets, the electric field intensity are in the same direction. Between the two sheets, that is between sheet 1 and sheet 2, the electric field intensity, they are in the same direction. And at the two sides of the two sheets, they are in the opposite direction. You can clearly see. Since electric field intensity is sigma by epsilon 0, look at this diagram. This sheet is having a plus Q charge, means this sheet will have a minus Q charge. Therefore, since the plate area and charge accumulation is same, I can say the surface charge density of this sheet is equal to the surface charge density of this sheet. If we are considering this diagram over to the parallel plate capacitor, you could clearly see the electric field intensity will only exist between the plates of the capacitor. Why I am saying the electric field intensity will only exist between the plates of capacitor? It is because between the plates of capacitor, the electric field intensity are in the same direction. They will get added up. At the two sides of the capacitor, the electric field intensity, they are in the opposite direction. They will get cancelled. Therefore, the total electric field intensity between the plates of the capacitor, the total electric field intensity between the plates of the capacitor, it will be sigma by 2 epsilon 0 plus sigma by 2 epsilon 0, and it is 2 sigma by 2 epsilon 0. I could write it as sigma by epsilon 0. This is the electric field intensity between the plates of the capacitor. The net electric field intensity between the plates of the capacitor is sigma by epsilon 0. Okay, now what is sigma? We know sigma is Q by A. Sigma is surface charge density, and surface charge density is charge per unit area. Therefore, I could write sigma as Q by A. Therefore, I could write electric field intensity as, instead of sigma, if I am replacing Q by A, I could write Q by A epsilon 0. This is the electric field intensity between the plates of the capacitor. Then, there is a relation between potential and electric field intensity. Hope you have learned that relation. That is, it was electric field intensity is the negative gradient of potential, and I could write V potential divided by distance. Electric field intensity is equal to potential divided by distance. This is a relation between electric field intensity and potential like this. Therefore, let me write it in an expanded manner. It is potential divided by distance. Therefore, what is potential then? Potential is equal to electric field intensity into distance. Then if I am using this relation to get the potential between the plates of the capacitor, I could write potential between the plates of the capacitor will be electric field intensity into distance between the plates. What's the distance between the plates? It is D. Okay, therefore potential is equal to electric field intensity into distance. V is equal to E into D. What's E? E is electric field intensity. Let's substitute the value of electric field intensity. Since we know the value of electric field intensity is Q by A epsilon 0, I could write V is equal to Q divided by A epsilon 0, that is for electric field intensity into V. This is potential. We have to determine the value of capacitance. Can you recall the basic expression for capacitance? Capacitance C is equal to Q by V. This was the basic expression for capacitance. Then let's substitute for the value of capacitance. Q is Q itself, divided by V means the reciprocal of this. Since this is V, we have to divide V means into A epsilon 0 divided by QD. That is the reciprocal of V. Okay, Q and Q will get cancelled. Therefore, C is equal to epsilon 0 A divided by D. This is one important expression, and this is the expression for capacitance of a parallel plate capacitor. Let's recall what's a parallel plate capacitor. It is an arrangement of parallel conducting sheets kept between an insulating medium. And between the plates of the parallel plate capacitor, the total electric field intensity will be sigma by 2 epsilon 0 plus sigma by 2 epsilon 0. This sigma by 2 epsilon 0 was obtained by electric field intensity due to a single sheet. That is an application of Gauss theorem. Okay, therefore it will be sigma by epsilon 0, where sigma is surface charge density. We could replace sigma as Q by A. Therefore, E is equal to Q by A epsilon 0. Then potential, we know electric field intensity equal to potential divided by distance. This is one basic relation that we are learning in the previous classes. Therefore, we could write potential is equal to electric field intensity into distance. In this case, the distance is D. Therefore, electric field intensity into D. We could substitute the value of electric field intensity as Q by A epsilon 0 into D. Therefore, we know the value of potential. And if we know the value of potential, we could substitute it in the basic expression of capacitance. The basic expression of capacitance is C is equal to Q by V. Instead of 1 by V, we are taking the reciprocal of V. That is A epsilon 0 divided by QD. Q and Q will get cancelled. C is equal to epsilon 0 A by D. Can I ask you what's A? A is the plate area of the capacitor. What is D? It is the distance between the capacitor. And what's the capacitance of a parallel plate capacitor? It is epsilon 0 A by D. What's the general expression for capacitance? It is C is equal to Q by D. What was the SI unit of capacitance? It is farad. Hope you have understood this. We'll stop this video right here. Okay.